Imagine a carousel, but one where the horses aren't fixed to poles. They swing wildly, crashing into each other, some flung off into the darkness, others spiraling into the central fire. This isn't a nightmare fantasy. This is the standard model for planetary systems across the galaxy. We see it everywhere we look. Giant hot Jupiter planets, worlds far larger than our own, don't orbit sedately like Jupiter does. They hurtle insanely close to their stars, completing entire orbits in mere hours, their atmospheres being blasted away in a perpetual 1,000-degree hurricane. We see twin stars locked in a lethal gravitational dance, one slowly cannibalizing the other, stripping it of its stellar material in a dazzling, deadly display. We see entire planets kicked out of their solar systems, doomed to wander the interstellar void as rogue, frozen worlds. Galaxies themselves, these colossal islands of billions of stars, don't simply coexist. They collide, ripping each other apart in a ballet of destruction that unfolds over millions of years. That is the norm. The chaos, the violence, the instability, that is the universe's default setting. And yet here we are. Why? The story of our survival starts not with life itself, but with the stage upon which it was allowed to emerge. That stage is Earth's orbit. It seems so simple, so fundamental, that we take it for granted. A year is 365 days. The seasons come and go with reliable regularity. We are on average 93 million miles from the sun. This consistency is the bedrock of our existence. But to understand how precious this stability is, I need to leave our cozy mental model behind and confront the reality of what an orbit truly is. An orbit is not a predetermined track in space, like a rail for a train. It is a continuous state of controlled falling. It is the manifestation of a perfect and perfectly fragile balance between two titanic forces. On one hand, you have the sun's gravity, an unimaginably powerful force that reaches out across millions of miles of empty space, pulling everything toward it with relentless determination. If this force acted alone, every planet, every asteroid, every speck of dust would be inexorably drawn into the sun, vaporized in its colossal furnace. The only thing stopping this from happening is the planet's own velocity. We are not sitting still in space, we are hurling through it. Earth is moving around the sun at an average speed of 67,000 miles per hour. This momentum fights the sun's pull, creating a perpetual tug-of-war. Gravity pulls us in. Our velocity tries to carry us away in a straight line. The result of this cosmic standoff is the curved path we call an orbit. We are forever falling towards the sun, but our speed ensures we constantly miss it. The shape of that path is everything. And this is where our incredible luck becomes apparent. Earth's orbit is almost, but not perfectly, circular. It's what we call an ellipse, but one that is so close to a circle, it's barely distinguishable. This near-perfect circle is the key to our stable climate. It means that throughout our year-long journey, our distance from the sun only varies by about 3 million miles. That small variation is enough to give us seasons, but not enough to boil or freeze us. I need you to truly feel the significance of this. Let's take a walk through our own solar system to see what happens when this balance is lost. When the orbit is not a gentle circle, but a violent, stretched oval. Our first stop is the innermost planet, Mercury. It's a scorched, cratered world, a place of extremes that defies imagination. Its orbit is a pronounced ellipse. At its farthest point, it's 43 million miles from the sun. But at its closest, it swings to within just 28 million miles. This wildly changing distance has profound consequences. Standing on the surface of Mercury at perihelion, its closest approach to the sun would be an instantaneous death sentence. The temperature soars to 800 degrees Fahrenheit. Lead would melt into puddles. But the heat is only part of the horror. Mercury has no substantial atmosphere to speak of, no protective blanket of gas. Without that atmospheric pressure, the fluids in your body would begin to boil at room temperature. Your blood, the saliva on your tongue, the moisture in your eyes, it would all vaporize. You wouldn't just die. You would quite literally explode. But the nightmare doesn't end there. As Mercury continues on its lopsided path and swings back out to its aphelion, the sun shrinks in the sky and the heat vanishes with shocking speed. In the eternal darkness of its long night, temperatures plummet to 300 degrees below zero, 3 times colder than the coldest temperature ever recorded on Earth. This is the most extreme temperature swing in the entire solar system, a daily cycle between a blast furnace and the void of deep space, all dictated by the shape of its path. And Mercury holds another orbital secret, one that reveals the dynamic, unstable nature of gravity itself. Isaac Newton envisioned a simple, predictable ellipse. But Albert Einstein showed us that gravity is more complex, the result of mass warping the very fabric of space and time. Mercury, being so close to the Sun's immense gravitational field, is a perfect test subject for this. Its orbit doesn't simply repeat. The point of its closest approach, its perihelion, slowly shifts over time. It's a minute change, but over thousands of years, if you were to map Mercury's path, it wouldn't trace a simple oval. It would draw a beautiful, daisy-like pattern around the Sun. It's a stunning visual proof that orbits are not static. They are dynamic, evolving things subtly influenced by the dance of gravity. Now, let's travel to the opposite end of the solar system, to the frozen dwarf planet, Pluto. Here, the problem isn't a changing distance in a tight orbit, but the sheer scale of the path itself. Pluto is so far away, so deep in the frozen outskirts of our system, that it takes 248 Earth years to complete a single orbit around the Sun. A year on Pluto is longer than the entire history of the United States as a nation. Its orbit is also highly elliptical, and even more bizarrely tilted on a different plane than the rest of the planets. For most of its long year, Pluto is a profoundly frozen world of ice and rock. But as its elliptical path brings it closer to the Sun, a strange summer begins. The feeble sunlight is just enough to warm the surface ices, causing them to sublimate, turning directly from solid to gas. For a brief, spectacular period, Pluto grows a thin, tenuous atmosphere, but summer doesn't last. As Pluto continues its slow trek back into the depths of space, the temperature plummets to 400 degrees below zero. The atmosphere itself begins to freeze. It doesn't rain, it snows. But this is no water snow. These are flakes of frozen nitrogen and methane, falling from a sky that is slowly collapsing. The gases that briefly envelop the world gradually freeze onto the surface, forming a glassy, semi-transparent layer of frozen air. Imagine a winter so profound that the very sky freezes and falls down upon you. That is the reality of Pluto's orbit, a 248-year cycle between a fleeting, wispy atmosphere and a sky-shattering deep freeze. Looking at Mercury and Pluto, I am struck by a profound sense of gratitude. We are perfectly positioned. Our orbit is a gentle ride. We get a consistent, life-giving dose of solar energy. We don't explode, we don't freeze solid, our atmosphere doesn't collapse onto the ground. We hit the orbital jackpot, but this jackpot is a delicate one. The margin for error is terrifyingly small. The difference between a life-sustaining orbit and a sterile one is a matter of a few percentage points in distance. To understand this, we need only look at our immediate planetary neighbors, Venus and Mars. Let's consider a nightmare scenario. What if Earth's orbit shifted slightly inward, pulling us closer to the Sun? The model for this hellish future is right next door: Venus. Venus is often called Earth's twin, similar in size and composition. But its orbit places it just a bit closer to the Sun, and that small difference triggered a cataclysmic runaway greenhouse effect. The result is a planetary inferno. The thick atmosphere, loaded with carbon dioxide, traps the Sun's heat with terrifying efficiency. The surface temperature on Venus is a constant 900 degrees Fahrenheit, hot enough to melt zinc. Its clouds are not made of water vapor, but of sulfuric acid. If our world were moved even a little bit sunward, the same fate could befall us. Our oceans would begin to evaporate, pumping vast quantities of water vapor, a potent greenhouse gas, into the atmosphere. This would trap more heat, evaporating more water, in a vicious cycle until our planet became a pressure cooker. The oceans would boil away entirely, leaving a scorching, barren desert under a crushing, toxic sky. Life would be utterly erased. We would die by fire. Now, let's consider the opposite. What if our orbit shifted slightly outward, away from the Sun? Our model for this is Mars. The red planet is a frozen, desolate world. Its thin atmosphere offers little insulation, and its surface temperatures average around 80 degrees Fahrenheit. If Earth were pushed further out, our fate would be one of ice, not fire. The process would be grimly straightforward. As we received less solar energy, the polar ice caps would begin to expand. Their brilliant white surfaces would reflect more sunlight back into space, a phenomenon known as the albedo effect. This would cause further cooling, expanding the ice even more. The feedback loop would accelerate. The oceans would begin to freeze at the poles, and then the sea ice would creep towards the equator. Eventually, the entire planet could become encased in a global ice sheet, a snowball Earth. The average global temperature could plunge to 50 degrees or lower. The complex machinery of our climate would shut down. The planet would enter a permanent, deep ice age. Life, if it survived at all, would be driven into tiny, desperate refuges around volcanic vents. We would die by ice fire or ice, the two ultimate extremes of planetary death. And the only thing standing between us and that fate is the precise, stable, circular path of our orbit, a path that has remained constant for over 4 billion years. That stability is not just a convenience. It is the absolute prerequisite for our existence. Consider the story of life on Earth. The first simple single-celled organisms emerged in the oceans around 3.5 to 4 billion years ago. For life to even begin, it needed a stable environment. The chemical reactions that led to the first self-replicating molecules, the formation of the first cell membranes, the slow, patient evolution of photosynthesis, these processes didn't happen in a day, or a century, or a millennium. They took hundreds of millions of years. They required a planet where the temperature, the liquid water, the chemical soup of the oceans remained within a narrow, hospitable band for epoch after epoch. That is a stability that only a circular orbit around a stable star can provide. The very DNA in every cell of your body is a testament to this cosmic stability. Its complex double helix structure is the product of billions of years of uninterrupted, peaceful evolution. It could not have assembled itself on a world like Mercury, where the surface is remelted every day, or on Pluto, where the very chemistry of life freezes solid for centuries. We are, quite literally, children of orbital harmony. But as I reflect on this incredible good fortune, a chilling thought begins to form in my mind. This stability we rely on, this perfect balance, how permanent is it? The orbits of Mercury and Pluto show us that paths can shift and change. The daisy pattern of Mercury is a tiny, subtle drift, but it is a drift nonetheless. Our solar system is not a static sculpture. It is a dynamic, evolving system. The planets tug on each other with their own gravity, creating tiny, resonant perturbations. Over millions of years, these tiny nudges can add up. Could the orbits of the giant planets, Jupiter, Saturn, Uranus, and Neptune, ever become unstable? Could their gravitational dance one day send a ripple through the inner solar system that disrupts our own perfect path? We are protected for now, nestled in our oasis. But the universe has a way of reminding us that chaos is the ultimate ruler. The evidence is written across the cosmos in the scars of galactic collisions and the frenzied orbits of alien worlds. Our solar system has enjoyed an unprecedented era of peace, but is it destined to last forever? Or is the violence that defines the rest of the universe simply waiting, biding its time before it finally reaches our doorstep? Imagine a spider, but one that weighs 4 million times more than our sun. Now imagine its web is not made of silk, but of space-time itself, a gravitational trap so vast it ensnares hundreds of billions of stars. Our sun, our planet, everything we know, is nothing more than a speck of dust caught in that web, orbiting a center we cannot see. For centuries, we looked at the gentle arc of the Milky Way and saw only wonder. We had no idea we were circling a predator. The first clues were subtle. Stars near the galactic center were seen moving at incomprehensible speeds, whipping around some unseen titanic mass at thousands of miles per second. They weren't orbiting empty space. They were orbiting a gravitational prison. Then we began to hear it. Not with our ears, but with our most advanced telescopes. A faint, rhythmic ticking of X-rays and radio waves, the death rattle of matter being ripped apart just before it vanished from our universe forever. We were listening to the feeding sounds of the beast. The question was no longer if it existed, but what it was, and how close we were to its event horizon, the point of no return. The journey to confirm the existence of this monster has been one of the greatest detective stories in the history of science. It began with a simple, almost childlike question. If the moon goes around the Earth and the Earth goes around the sun, then what does the sun go around? Astronomers asked this for generations, peering into the dense, dusty core of our galaxy, trying to glimpse what lay at the center of the great stellar carousel. The center of the Milky Way is a place obscured from our view by vast clouds of interstellar dust and gas. Visible light cannot penetrate this cosmic murk. It's like trying to see the details of a distant city through a thick, perpetual fog. To solve this mystery, we needed new eyes. We had to learn to see the universe not in the light we see, but in the light we cannot. We turned to infrared telescopes, which can peer through the dust, and radio telescopes, which can listen to the unique signatures of celestial objects. What we found was astonishing. At the very heart of the galaxy, there is a densely packed swarm of millions of stars, a stellar beehive buzzing with frantic energy. These stars are not like our serene sun. They are trapped in a gravitational madhouse orbiting at ferocious speeds around a tiny, dark point in space. The sheer velocity of these stars was the first major clue to the monster's mass. By applying the laws of gravity, we could calculate the mass of the object they were orbiting. The answer was staggering. Contained within a region of space smaller than our solar system was a mass equivalent to 4 million suns. There was only one thing in the known universe that could be so unimaginably dense, so terrifyingly massive, a supermassive black hole. We named it Sagittarius A. But naming it and understanding it are two very different things. To truly prove its nature, we needed to see it. Not the black hole itself, for no light can escape it, but its shadow, the telltale void it creates against the glowing background of hot gas and stars. This was a challenge of almost impossible precision. One astronomer described it to me as the ultimate cosmic needle in a haystack search. My journey to understand this beast led me to the summit of Mauna Kea in Hawaii, to one of the most powerful telescopes on Earth. Here, at the W.M. Keck Observatory, a team of astronomers, led by the tenacious Dr. Andrea Ghez, has spent over 15 years on a single, monumental task, mapping the orbits of stars at the very heart of our galaxy. The region which we have to study to prove that there's a black hole is incredibly small. It is absolutely the case of looking for a needle in a haystack. Except we know exactly where the needle is. To be able to do this experiment, one has to be able to see the stars that are very close to the center of the galaxy and to position them incredibly accurately. And this would be equivalent to me in Los Angeles looking at you in New York and seeing you be able to move your finger like this. The turbulence in our own atmosphere blurs and distorts the light from these distant stars, making precise measurement impossible. To overcome this, Keck uses a revolutionary technology called adaptive optics. A powerful laser beam is fired into the sky, creating an artificial guide star. Sensors detect how this laser beacon is distorted by the atmosphere, and then, hundreds of times a second, motors adjust the telescope's huge 30-foot mirror, canceling out the blurring effect. It is like putting glasses on the telescope, giving it crystal clear vision. Night after night, year after year, the team took snapshots of the galactic center. When they strung these images together into a time-lapse movie, they witnessed something extraordinary. The stars weren't just moving, they were racing. One star in particular, which they designated S2, was moving at a blistering 11,000 miles per second, over 3% the speed of light, as it swung around its closest approach to the invisible point. Its orbit was a perfect elliptical path, and at the focus of that ellipse was nothing. Empty space with the mass of 4 million suns. This was the final irrefutable proof. We were watching stars dance around a monster, But what exactly is this monster? To comprehend Sagittarius A, I first had to understand the nature of black holes themselves. The concept is born from Einstein's theory of general relativity, which describes gravity not as a force, but as a warp in the fabric of space-time. Imagine space-time as a stretched, taut rubber sheet. A massive object like a star creates a dip in that sheet. Planets orbit by rolling around the rim of that dip, like marbles. But a black hole is different. It's an object so massive and so dense that it doesn't just create a dip. It punches a hole right through the rubber sheet. It creates a bottomless pit in space-time. The boundary of this pit is what we call the event horizon. This is not a physical surface you could stand on. It is a mathematical point of no return, the edge of the known universe. Once anything, matter, light, even information, crosses that threshold, it can never come back. It is lost to us forever, dragged down into the singularity at the center, the singularity. This is the true heart of the monster, a word that barely conceals our ignorance. According to the mathematics, it is a point of infinite density, where all the mass of the black hole is crushed into a volume of zero size. Here, the warping of space-time becomes infinite, and the laws of physics as we know them simply cease to exist. It is a place where our understanding of reality ends. A singularity is a point of infinite gravity, where space and time become meaningless. Now that is ridiculous. A singularity is basically a word for saying I don't know. While we may not understand the singularity, we understand the horrors that await anything that ventures too close to the event horizon. The force you would experience is unlike anything in our universe. It's a process with a chillingly vivid name, spaghettification. Let's conduct a thought experiment. Imagine we are brave or foolish enough to send a robotic probe on a one-way mission to Sagittarius A. As it approaches the event horizon, it begins to fall feet first. Its feet are closer to the black hole than its head, and because gravity weakens with distance, the pull on its feet is exponentially stronger than the pull on its head. As you fall into a black hole, feet first, your feet are closer to the black hole, and so the gravity they feel is stronger. Your head is not quite as close, and so the gravity it feels is less. And basically what happens is you get stretched out. Your feet are being pulled much harder than your head, and you're like a piece of taffy being pulled between two strong people. As you get thinner and thinner and thinner, as you get closer and closer and closer, you're undergoing a process we call spaghettification because you're basically turned into a long, thin tube of pasta. Our robotic probe, built of the strongest materials known to science, would be stretched, compressed, and torn apart long before it reached the event horizon. It would be transformed from a sophisticated machine into a stream of elementary particles, a ghostly noodle of atoms spiraling into the abyss. But let's imagine, for a moment, that our probe is indestructible. As it gets closer to the event horizon, even stranger things begin to happen. Gravity is so extreme here that it doesn't just warp space, it warps time itself. According to Einstein's theories, gravity is a brake on time. The stronger the gravity, the slower time passes. We think of time as being endless. However, in a black hole, in some sense, time stops. This sounds like it's nuts, but that's the way it works. It's in the math. It's actually woven into the fabric of the universe itself. If we were to watch the probe from a safe distance through a powerful telescope, we would witness a cosmic freeze frame. As the probe approaches the event horizon, it would appear to slow down. Its clock would be ticking infinitely slowly compared to ours. It would seem to hover, frozen forever at the threshold, its image becoming redder and dimmer until it faded from view entirely. We would never actually see it cross the event horizon. From our perspective, outside the black hole, that moment is stretched out to infinity. You actually can never observe an object fall all the way through the event horizon. It literally freezes at the surface because its clock is going infinitely slowly compared to yours. But for the probe itself, time passes normally. In a flash, from its own perspective, it would cross the boundary. If it could point its cameras backward, toward the universe it left behind, it would see a final, breathtaking view. The light from the entire cosmos would be bent into a single, blindingly bright circle directly behind it, the entrance to the hole having shrunk to a pinhole of light. And then it would be gone. The universe as we know it would be lost forever. Ahead, only the infinite darkness of the singularity. This is the nature of the beast at the center of our galaxy. A supermassive black hole is not just an object. It is a fundamental boundary to reality. It is a cosmic vacuum cleaner, a destroyer of worlds, a prison from which not even light can escape. And yet, as terrifying as Sagittarius A is, it is also our anchor. Its immense gravity is the glue that holds the Milky Way together. Without its 4 million solar mass grip, the stars in the inner galaxy would fly apart, scattering into the intergalactic void. The monster is both destroyer and creator. It is the architect of the galactic order we see, the silent, invisible king on a throne of darkness. But kings can be unpredictable. For now, Sagittarius A is relatively quiet, a sleeping giant. It feeds on only a trickle of gas and the occasional unlucky star. But we have evidence from other galaxies that when black holes feed aggressively, they become the most violent objects in the universe. They can unleash jets of energy and radiation millions of light years long, capable of sterilizing entire galaxies, shutting down star formation, and sculpting the evolution of the cosmos itself. This forces me to confront a new and deeply unsettling reality. Our solar system's stability, the very oasis I marveled at in the first chapter, exists only with the permission of this distant monster. We are safe only for as long as it slumbers. Imagine a bomb so vast it could engulf every planet out to the orbit of Mars, a bomb with a fuse 7 billion years long, silently burning down since before our planet was even born. We orbit that bomb. We bask in the energy of its slow, steady detonation. For now, the forces within it are in a perfect, life-giving balance. But that balance is temporary. Deep within its core, the sun is burning through its fuel at a rate of 600 million tons every second. And when that fuel runs out, the balance will shatter. The sun will transform from a source of life into a force of absolute annihilation. It will swell into a bloated, angry red giant, its outer atmosphere licking at the edges of our world. The oceans will boil away into space. The mountains will flow like rivers of molten rock. The very Earth, the only home we have ever known, will be consumed, vaporized, its atoms scattered into the stellar wind. This isn't a speculative disaster movie plot. This is astrophysics. This is the inevitable future of our world, dictated by the life cycle of a perfectly ordinary star. The clock is ticking. The question is not if it will happen, but what we will see in the final terrifying days. To understand the sun's future, I first had to confront its present violence. We see a placid yellow disk, but that is a lie painted by distance. Through the eyes of solar observatories, like the Solar Dynamics Observatory, SDO, and the SOHO satellite, I have seen the sun's true face. It is a roiling, turbulent sea of superheated plasma, a cauldron of magnetic fury. The key to this violence is magnetism. The sun is a gigantic dynamo. Its differential rotation, spinning faster at the equator than at the poles, twists and stretches its internal magnetic fields like cosmic taffy. These fields become tangled, storing immense amounts of energy. When the tension becomes too great, the fields snap, realigning in a cataclysmic release of power. We call this a solar flare. One flare, one of the most energetic flares on the surface of the sun, would be equivalent to over 200 million hydrogen atomic bombs. It's enough energy to power the entire human race's energy consumption for something like 2 million years. A single solar flare can be as bright as 400 billion trillion light bulbs. But the visible light is just the tip of the spear. These explosions unleash a full spectrum of lethal radiation, radio waves, intense ultraviolet, and even X-rays. Within minutes, a torrent of high-energy particles, the solar wind, is blasted into space at millions of miles per hour. When this storm hits Earth, it can cripple satellites, knock out power grids, and bathe astronauts in dangerous radiation. It is a constant reminder that we live in the crosshairs of a tempestuous star. But these flares, as powerful as they are mere firecrackers compared to the sun's ultimate fate. They are the day-to-day tantrums of a star in its prime. The true cataclysm begins when the star starts to die, and the death of a star is a battle between two fundamental forces that have been locked in a stalemate for billions of years: the outward pressure of nuclear fusion and the inward crush of gravity. For now, in the sun's core, fusion is winning. In a furnace heated to 15 million degrees Celsius and crushed under unimaginable pressure, atoms of hydrogen are forced together to create helium. This process releases the photons that eventually, after a 100,000-year journey, become the sunlight that warms our skin. This energy pushing outward perfectly balances the sun's own gravity, which is trying to collapse it inward. This balance is called hydrostatic equilibrium, and it is the reason the sun has maintained its stable size for so long. But this balance is predicated on a finite resource: hydrogen fuel. Every second, it burns through 600 million tons of the hydrogen fuel in its core. At that rate, the hydrogen will run out in about 7 billion years. The sun is a ticking clock, and the fuel gauge is dropping. This is the pivot point, the moment the universe's violent nature turns its full attention to our world. The end begins not with a bang, but with a sputter. In about 5 billion years, the hydrogen in the sun's core will finally be exhausted, leaving behind a core of inert helium, a celestial ash. In that moment, the balance of power shifts decisively to gravity. With the outward pressure of fusion from the core suddenly diminished, gravity seizes its chance. It begins to crush the star inward with relentless force. But this collapse has a paradoxical effect. As the core contracts, it heats up dramatically. This heat spreads to the shell of hydrogen still surrounding the core, which is now subjected to even more intense heat and pressure than before. Fusion in this shell ignites with a vengeance, burning far more fiercely than it ever did in the core. This massive new surge of energy has a dramatic effect on the star's outer layers. When you heat up a gas, it expands, and so the sun will actually expand up. Instead of being 1,000,000 miles across like it is now, it'll swell up until it's about 100 million miles across. Our sun will become a red giant. Our sun will transform. It will bloat into a monstrous red giant. Its surface will cool, turning a dull, bloody red, but its size will make it impossibly luminous. The sun will swell until it consumes the orbits of Mercury and Venus. Their rocky bodies will be vaporized in an instant, adding their substance to the star's expanding atmosphere. And then it will be Earth's turn. Let me describe the last days of Earth. It will not be a swift death. It will be a slow, agonizing descent into hell. The first sign will be the changing sun. It will no longer be a discrete disk in the sky. It will be a swollen, bloated orb slowly creeping over the horizon. Imagine a sunrise 7 billion AD. It's not just a little yellow disk coming up all cheerful and nice. What you would see is a huge, swollen, bloated red disk slowly reaching up over the horizon. And when the sun is fully up in the sky, it's blasting down heat on the earth. It would be like sticking your head in an oven set to broil. The temperature on Earth will begin to climb, not by degrees, but by tens, then hundreds of degrees. The polar ice caps will vanish in a matter of days. The oceans will start to steam, creating a global suffocating humidity. The sky will turn a hazy, sickly orange. Weather patterns will go insane, with superstorms of unimaginable fury scouring the continents. Then, the boiling point will be reached. The oceans, the cradle of life, will begin to boil. Not in isolated geysers, but globally. A roaring, thick steam will fill the atmosphere, a planetary sauna that will cook all remaining life. The mountains, forged over billions of years of tectonic activity, will not stand as monuments to our world's endurance. They will begin to soften, then melt, flowing in great glowing rivers of magma across the planetary surface. Oceans will boil, the mountains will melt, and we'll have the last nice day on the planet Earth. And then, the final act. The sun, now a true behemoth, will have expanded to its maximum extent. Its tenuous outer atmosphere will finally reach the orbit of Earth. Our planet will no longer be a separate world. It will be inside the sun. There will be no impact, no colossal collision. The Earth will begin to plow through the sun's outer layers, a speck of rock moving through a fog of star stuff. But even this faint resistance will be enough. The Earth's orbital velocity will be slowed by drag. Like a satellite falling from orbit, it will begin a slow, decaying spiral into the inferno. It will be a funeral pyre on a cosmic scale. The iron core of our planet may survive for a time, a glowing ember sinking through the layers of the star, but eventually it too will be assimilated, its atoms scattered and fused in the sun's core. Every mountain, every ocean, every memory of every living thing that ever existed on Earth will be returned to the star from which it came. But the sun's self-destruction does not end with the death of Earth. The red giant phases one of profound instability. The core, now a blazing ball of helium, continues to be crushed by gravity. When it reaches a critical temperature of 100 million degrees, a new, more violent fusion process ignites, helium fusion. In a cosmic paroxysm known as the helium flash, the sun's core will fuse helium into carbon in a runaway thermal explosion that lasts mere minutes. This blast will send titanic shockwaves through the star. The sun will become a cosmic yo-yo, pulsating violently as it struggles to find a new equilibrium. With each pulse, it will blow away its own outer layers into space. Great shells of gas, glowing with the light of the exposed, dying core, will expand outwards, creating a beautiful, ethereal structure known as a planetary nebula. For a few tens of thousands of years, the ghostly glow of this nebula will be a tombstone in the galaxy, a final, beautiful testament to the star that was. All that will be left of the sun is its core. No longer able to sustain fusion, it will be crushed by gravity into a dense Earth-sized ball of carbon and oxygen, a white dwarf. It will be a stellar cinder glowing with residual heat for billions of years before finally cooling into a cold, black diamond in the void, a black dwarf. The cycle will be complete. This narrative of our star's death is not just a story about the sun. It is the story of nearly every star in the sky. I look up at the familiar constellations, Orion, Cygnus, Ursa Major, and I no longer see patterns. I see graveyards and future funeral pyres. I see stars in every stage of this violent life cycle. This knowledge forces a profound and unsettling perspective. The very processes that create the elements necessary for life, the carbon in our cells, the oxygen in our lungs, are forged in the violent deaths of stars. We are literally stardust, but the same physics that created us will also inevitably destroy us. Our existence is a fleeting, beautiful moment of calm in a storm of cosmic violence that has raged for billions of years and will continue for billions more. We are living on borrowed time, in a temporary oasis under a friendly-faced killer. The sun's stable middle age, which has allowed for the entire history of life on Earth, is the briefest of interludes in its destructive life story. Chapter 4. Imagine a single star, a steady beacon in a distant galaxy. For millions of years it has burned, a constant point of light. Now imagine that point of light suddenly, without warning, beginning to brighten. In less than a day, it outshines every other star in its galaxy combined. In its final defiant act, it releases more energy than our sun will over its entire 10 billion-year lifespan. For a few weeks, it is a second sun in that distant island of stars, a titanic flashbulb popping in the cosmic dark. Then, just as quickly, it fades, leaving behind an expanding cloud of glowing debris and, at its heart, a bizarre, ultra-dense corpse. This is not science fiction. We see these events regularly scattered across the universe. They are the universe's way of recycling, of building anew through total destruction. But this cosmic forge is also a weapon of unimaginable power. If one of these detonations were to happen too close to Earth within a few dozen light years, the blast of radiation would be like a celestial shotgun aimed directly at our planet. It would strip away our atmosphere, scour the surface with ultraviolet and X-ray radiation, and trigger a mass extinction that would make the dinosaur-killing asteroid look like a trivial event. The question is not if a supernova will occur in our galactic neighborhood. but when. To understand the supernova, I first had to understand the life of the stars that are destined for this spectacular end. Not all stars die this way. Our Sun, a modest middle-class star, will end its life relatively quietly as a planetary nebula and a white dwarf. The stars that become supernovae are the true aristocrats and the tragic giants of the stellar world. They live fast, burn bright, and die young. There are two primary paths to a supernova, two different triggers for the same universe-shattering explosion. The first involves the most massive stars in the cosmos. Think of a star like a cosmic pressure cooker. For its entire life, the outward pressure from fusion in its core fights against the inward crush of its own gravity. In a massive star, that gravity is immense. To fight it, the star has to burn its nuclear fuel at a ferocious rate. A star 10 or 20 times more massive than our Sun is a profligate spendthrift. It consumes its hydrogen fuel in just a few million years, a mere blink in cosmic time compared to our Sun's 10 billion-year life. As it runs out of one fuel, its core, crushed by gravity, heats up enough to start fusing the next element in the chain. Helium into carbon, carbon into oxygen, and so on, like a layered onion. At its heart, a forge of incredible violence creates heavier and heavier elements: neon, magnesium, silicon. This process continues until the star's core is a ball of iron, and here, the star hits a cosmic wall. Fusing iron does not release energy. It consumes it. It is a nuclear dead end. In an instant, the star's central engine shuts off. The balance of billions of years is shattered. With no outward pressure from fusion to support it, the iron core is defenseless against the monumental weight of the star's outer layers. Gravity wins the war in a fraction of a second. The core collapses. In less than a second, a core the size of Earth is crushed into a sphere of ultra-dense matter just a dozen miles across. The collapse is so rapid, so violent, that it triggers a rebound effect. A devastating shock wave blasts outward from the newborn core, ripping through the still infalling outer layers of the star. The energy released in this rebound is almost beyond comprehension. The star is torn apart from the inside out. The shockwave, superheated to billions of degrees, triggers a final frantic wave of nuclear fusion throughout the star's disintegrating body, creating elements heavier than iron, gold, silver, uranium, and flinging them into the interstellar void at nearly the speed of light. This is the supernova. The star's outer layers are ejected into space, forming a beautiful, expanding nebula that will one day become the raw material for new stars and planets. But what of the crushed core? Its fate is equally extreme. The force of the collapse is so great that it can forge one of two bizarre and terrifying objects. If the core is between about 1.4 and 3 times the mass of our Sun, the collapse is halted by a quantum mechanical force known as neutron degeneracy pressure. The protons and electrons are crushed together to form neutrons. The result is a neutron star, a city-sized object so dense that a single teaspoon of its material would weigh billions of tons. It spins rapidly, often beaming radiation like a cosmic lighthouse. We call these pulsars. If the core is more than about 3 solar masses, not even neutron degeneracy pressure can stop the collapse. Gravity becomes absolute. The core collapses all the way down to a singularity, birthing a black hole. The supernova is thus both a creator and a destroyer on the grandest scale. It seeds the galaxy with the elements for life and simultaneously creates the ultimate abyss. The second path to a supernova is perhaps even more insidious. It involves a stellar partnership, a cosmic dance of death between two stars orbiting each other. One of them is a white dwarf, the exposed core of a sun-like star that has already ended its life. A white dwarf is a fantastic object. It's essentially a ball of carbon and oxygen, supported by quantum forces. But it has a limit. If you add more mass to it, pushing it over about 1.4 times the mass of our Sun, it can no longer support itself. In a binary system, a white dwarf can be a vampire. Its powerful gravity can slowly siphon material away from its companion star. With every ounce of stolen gas, the white dwarf grows heavier, edging closer to that critical mass limit, the Chandrasekhar limit. As it approaches this threshold, the pressure and temperature in its core skyrocket. Suddenly, the carbon, which has been inert for billions of years, ignites. But this is not the controlled fusion of a living star. This is a runaway thermonuclear explosion. The fusion flame rips through the entire white dwarf in a matter of seconds. There is no shockwave, no collapsing core. The entire star is vaporized in a titanic nuclear fireball. This is a Type Ia supernova, a total stellar detonation. Because these explosions always happen at roughly the same mass, they have a standardized brightness, making them standard candles that we use to measure the vast distances of the universe. It was by observing these supernovae that astronomers made the shocking discovery that the expansion of the universe is accelerating, driven by a mysterious force we call dark energy. The aftermath of a supernova is a place of both creation and utter devastation. The expanding shock wave from the explosion plows into the surrounding interstellar medium, compressing gas and dust and triggering the collapse of new nebulae to form the next generation of stars. Our own solar system formed from such a cloud, enriched by the heavy elements cast out from long-dead supernovae, the iron in the Earth's core, the gold in our jewelry, the uranium that fuels our power plants. All of it was forged in the heart of a star that died a violent death billions of years ago. We are, in the most literal sense, children of the stars, or more accurately, children of stellar cataclysm. But this creative force has a dark side, a lethal range. A supernova is a directional event. Along with the expanding shell of debris, it fires two jets of intense radiation, gamma ray bursts, from its poles. These are the most energetic electromagnetic events known in the universe. If a nearby supernova, within 50 light years or so, were to point one of these jets at Earth, the consequences would be apocalyptic. The gamma rays and cosmic rays would smash into our upper atmosphere, breaking apart nitrogen and oxygen molecules and creating a toxic smog of nitrogen oxides. This would chemically destroy the ozone layer, leaving life on the surface exposed to the sun's full, deadly ultraviolet radiation. The sky would glow with an eerie, perpetual light show, while the radiation would directly damage the DNA of virtually every living thing on the planet. It would trigger a mass extinction event, potentially ending all complex life. Evidence suggests this may have happened before. Some scientists hypothesize that a minor mass extinction event about 450 million years ago, the Ordovician-Silurian extinction, could have been caused by a nearby gamma-ray burst from a supernova. This knowledge transforms my view of the night sky. Every bright, massive star I see, Betelgeuse in Orion, a red supergiant on the brink of collapse, is not just a beautiful light. It is a potential bomb. Its death throw could be the most significant astronomical event for our planet in millions of years. We are living in a cosmic shooting gallery where the bullets are the dying screams of stars. The supernova is the ultimate expression of the universe's violent nature. It is an engine of destruction that is also the only source of creation complex enough to build a world like ours and the life upon it. It is the end of one story and the violent, necessary beginning of another. Imagine two cities, each containing hundreds of billions of citizens, each with their own streets, their own power grids, their own delicate balance. Now, hurl these two cities at each other at 1,000,000 miles an hour. But this is no ordinary crash. This is a collision in slow motion, a ballet of destruction that unfolds over hundreds of millions of years. The citizens, the stars, are so far apart they rarely touch. Yet, their world is utterly transformed. The gravitational pull of the passing galaxies stretches them like taffy, weaving great tidal tails of stars into the emptiness. Their delicate spiral arms are shredded, their structures erased. Within their colossal clouds of gas and dust, the collision triggers a firestorm of starbirth, thousands of new suns igniting every year, their fierce radiation boiling away the planetary cradles around them. And at the heart of this chaos, the two supermassive black holes. The monsters I once feared in isolation begin a lethal dance, spiraling toward each other until they finally merge in an event so violent it shakes the very fabric of space-time. sending gravitational waves pulsing across the cosmos. This is not a rare event. It is the norm. It is how galaxies grow, evolve, and die. Our own Milky Way is a cannibal littered with the remnants of smaller galaxies it has consumed. And in 4.5 billion years, it will meet its match. We are on a collision course with the Andromeda galaxy. The future of our night sky and the very existence of our solar system hinges on this ultimate cosmic violence. To comprehend the violence of a galactic collision, I first had to shed my earthbound perspective of what a collision means. In the vacuum of space, there is no sound, no fireball, no single moment of impact. It is a gravitational war, a slow-motion rearrangement of the cosmos driven by the most pervasive force in the universe. The process begins gently, almost imperceptibly. As two galaxies, like our Milky Way and Andromeda, first feel each other's gravitational pull, they begin to accelerate toward one another. For millions of years, they simply look larger in each other's skies. But as they close in, the real destruction begins. The force of gravity is not uniform. The near side of each galaxy feels a stronger pull than the far side. This difference, the tidal force, starts to stretch and distort the majestic spiral structures. What you get are these incredible tidal tails, great streams of stars, gas and dust being pulled out of the galaxies and flung into intergalactic space. It's like pulling taffy. The galaxies lose their identity long before their stars ever intermingle. They become these distorted, messy, beautiful wrecks. Through powerful telescopes like the Hubble, I have seen these wrecks. They have names like the Mice or the Antennae galaxies, their long, luminous tails stretching across hundreds of thousands of light years. They are ghostly scars of the gravitational battle. Within the galaxies themselves, the orderly rotation of stars is thrown into chaos. A star like our Sun, cruising along a predictable circular orbit, can be flung into a new highly elliptical path, or even be ejected entirely from the galaxy to become a lonely rogue star, wandering the intergalactic void forever. Our solar system could be thrown from the suburbs of the new galaxy into the chaotic inner core, or cast out into the freezing darkness between galaxies. But the gravitational chaos is only half the story. The real fireworks, the true engine of both creation and destruction, involves the galaxy's gas and dust. While stars mostly pass by each other unscathed, the colossal clouds of interstellar gas and dust slam into each other at phenomenal speeds. These collisions are unlike anything we know on Earth. The clouds compress, their density skyrocketing. This triggers a ferocious burst of star formation, a phenomenon known as a starburst. In a normal galaxy like our Milky Way, maybe 1 or 2 new stars are born per year. In a colliding galaxy, that rate can explode into the thousands. It's a firestorm of creation, but it's a violent, unsustainable firestorm. These aren't gentle, long-lived stars like our Sun. These are massive, blue, hot stars that live fast and die young. These newly formed massive stars burn through their fuel in just a few million years, ending their lives not with a whimper, but with a bang, as supernovae. The combined effect of thousands of these explosions within a relatively small volume of space is catastrophic. They create immense superbubbles and shock waves that heat the surrounding gas to millions of degrees, preventing it from cooling and forming new, quieter generations of stars. They blast the galaxy's remaining gas and dust out into space, effectively starving the galaxy of the raw materials for future star formation. A colliding galaxy is thus committing a form of stellar suicide, using up its entire future in a brief, glorious, and violent burst of activity. This starburst phase is the most visually spectacular and energetically intense period in a galaxy's life. The combined light from all the new, massive, hot stars can outshine the rest of the galaxy. The dust, heated by this intense radiation, glows brightly in the infrared, making these colliding galaxies some of the brightest objects in the universe at those wavelengths. Yet, amidst this chaos, the most profound and violent event is yet to come. It is a meeting I have been anticipating since I first learned of the monster in our own galactic core. At the heart of every large galaxy lies a supermassive black hole. As the galaxies merge, their central black holes begin their own deadly dance. Initially, they orbit each other at a great distance, but as they lose energy through gravitational interactions with stars and gas, they spiral inward. This is a slow process, taking tens or even hundreds of millions of years. Eventually, they form a binary pair, two monsters locked in a tightening orbit. The final act is the merger. As the black holes close to within a few light years of each other, they begin to lose energy in a new and dramatic way by emitting gravitational waves. These are ripples in the fabric of space-time itself, first predicted by Einstein. As the black holes whip around each other at a significant fraction of the speed of light, they churn the space-time around them, sending these waves out across the universe. The closer they get, the more energy they lose and the faster they spiral in. In the last few seconds before the merger, their orbits become a frenzied whirl, and the gravitational waves they emit carry away as much energy in a single burst as all the stars in the observable universe combined. Then they merge. In a fraction of a second, two singularities become one. The new, larger black hole that forms is initially lopsided, vibrating like a struck bell, but it quickly settles down, emitting a final burst of gravitational waves. This event, the collision of two supermassive black holes, is the single most powerful explosion since the Big Bang, a silent scream of space-time that echoes through the cosmos. The aftermath of a galactic merger is a new kind of galaxy. The beautiful structured spirals are gone. What remains is often a featureless elliptical galaxy, a vast red and yellow swarm of older stars, a galactic retirement home. The starburst has burned out, the gas has been expelled or used up, and star formation has effectively ceased. The galaxy is quiescent, its violent youth behind it. This cosmic cycle is not some distant abstract concept. The evidence is all around us. Our own Milky Way is currently digesting several smaller galaxies it has cannibalized in the past. The Sagittarius dwarf spheroidal galaxy is being torn apart by our galaxy's gravity, its stars strewn across our sky. And the future is written in the motions of the stars. The Andromeda galaxy, our largest galactic neighbor, is hurtling towards us at about 250,000 miles per hour. The collision is inevitable. In about 4.5 billion years, the Milky Way and Andromeda will begin their first close pass. They will swing by each other, their gravity causing catastrophic distortions. Over the next billion or 2 years, they will swing back and forth, eventually merging into a single, giant elliptical galaxy. We've named it Milkomeda. What will this mean for our solar system? The odds are surprisingly good that our Sun and Earth will survive the stellar traffic jam. The spaces between stars are so vast that the chance of our solar system being destroyed by a direct stellar collision is negligible. However, we will not be untouched. There is a significant chance that the gravitational turbulence could fling us out of the galaxy entirely into the intergalactic void. A more likely and still dramatic fate is that we will be relocated to the outer reaches of the new elliptical galaxy, far from the chaotic core. The night sky from Earth during the merger will be transformed beyond recognition. The familiar band of the Milky Way will be warped and torn. Andromeda, now a looming, distorted smear, will grow to dominate the heavens. As the gas clouds collide, the sky will fill with the pink glow of 1 trillion newborn stars, igniting in a final glorious starburst. It will be the most spectacular and terrifying light show in the history of our planet. This knowledge completes a profound and humbling cycle. I began by marveling at the stability of Earth's orbit, our local oasis. I then discovered the violent forces that govern stars and black holes. Now I see that even these colossal structures are temporary, subject to a violence on a scale that dwarfs them all. The universe is a place of perpetual, hierarchical violence. Planets orbit stars, stars orbit black holes, and galaxies collide in a dance of creation and destruction that shapes the evolution of the cosmos itself. Imagine compressing every single galaxy, star, planet, and speck of dust in the entire observable universe, hundreds of billions of galaxies, each with hundreds of billions of stars, into a space trillions of times smaller than a single atom. Now imagine this infinitesimal point, this universe in a nutshell, suddenly and catastrophically exploding into existence. Not into space, but as space, unfurling faster than the speed of light. In the first second of its life, the universe was a seething, chaotic broth of energy so intense that matter could not even form. It was a war zone where the fundamental forces of nature, gravity, electromagnetism, the strong and weak nuclear forces, fought for dominance, freezing out of a unified superforce in a series of cosmic phase transitions that shattered the symmetry of the newborn cosmos. This wasn't a fireball in a void. It was the creation of the void itself. And within that first unimaginable fraction of a second, the blueprint for all future cosmic structure, the galaxies, the clusters, the great cosmic web, was imprinted onto the fabric of reality as microscopic quantum fluctuations, stretched to astronomical sizes by a period of hyperinflation. The universe was born in a state of ultimate violence, and that violence is its defining characteristic. The echo of that first instant is still with us, detectable as a faint cold whisper of microwave radiation that permeates all of space. We are still inside the bubble of that first cataclysm. The journey to understand the Big Bang is not a journey to a place, but to a state of such extreme energy and density that our current laws of physics break down. We cannot see the Big Bang itself. It is hidden behind a veil, a wall of opacity. But we can trace the universe's expansion back to its hottest, densest phases, and we can observe the aftermath. The first and most profound piece of evidence is the expansion itself. In the 1920s, Edwin Hubble made the startling discovery that nearly all galaxies are moving away from us, and the farther away they are, the faster they're receding. The universe is not static, it is stretching. Running the film backward in time, everything converges to a single point of infinite density, a singularity. This was the first clue that our universe had a beginning. The second piece of evidence is the cosmic microwave background, CMB radiation. In 1965, two astronomers accidentally discovered a faint, uniform glow of microwave radiation coming from every direction in space. This is the remnant heat of the Big Bang. As the universe expanded and cooled, about 380,000 years after the initial explosion, it cooled enough for electrons and protons to combine into neutral hydrogen atoms. This moment, called recombination, made the universe transparent for the first time. The light that was finally set free has been traveling ever since, stretched by the expanding universe from visible light into microwaves. This is the oldest light we can see, a baby picture of the cosmos. But this baby picture is not perfectly smooth. When we look at the CMB with exquisitely sensitive instruments like the Planck satellite, we see tiny variations in temperature, tiny ripples in the fabric of space-time. These ripples are the seeds of all future structure. They are the gravitational blueprints for the first stars, the first galaxies, and the great cosmic web, and they point to a violent origin. To understand how these seeds were planted, I must venture into the very first instance of time. The standard Big Bang model describes the universe's evolution from a hot, dense state, but it doesn't explain the initial conditions. Why was the universe so perfectly uniform on large scales? Why is its geometry flat? The answer, we believe, is a process of unimaginable violence called cosmic inflation. The concept of inflation is mind-bending. In the first fraction of a second, perhaps 1036 seconds after the beginning, a bizarre form of energy, a scalar field, dominated the universe. This energy caused the fabric of space-time to expand exponentially, inflating a subatomic volume of space to a size larger than our observable universe in a time so short it has no analog in human experience. During this inflationary epoch, the universe doubled in size every 10^38 seconds or less. This hyperexpansion solved several major puzzles. It stretched the universe to incredible smoothness, just as blowing up a balloon smooths out wrinkles on its surface. It made the geometry flat, and most importantly, it took the microscopic quantum fluctuations that were inherent to that energy field and stretched them to macroscopic sizes. These stretched quantum fluctuations became the density variations, the slightly denser and less dense regions that we see in the CMB. The gentle ripples in the CMB are the magnified fingerprints of quantum violence, the primordial tremors that would, over billions of years, gravitationally collapse to form everything we see. Inflation was a violent, non-negotiable reshaping of the cosmos. When it ended, the energy that had driven it decayed, flooding the universe with a hot, dense plasma of fundamental particles, quarks, gluons, leptons. This was the hot Big Bang proper. The universe was now a seething, opaque soup, so dense that light could not travel freely. The next few moments were a series of violent phase transitions. As the universe cooled and the fundamental forces we know today froze out from their primordial unity, the strong nuclear force separated, then the weak nuclear force and electromagnetism split. With each transition, the universe's symmetry was broken, releasing immense energy in a process that may have created the matter-antimatter asymmetry we see today. We live in a universe made of matter, but our best theories suggest that the Big Bang should have created equal amounts of matter and antimatter, which would have annihilated each other, leaving behind a universe of pure light. Something happened, a violent process that violated CP symmetry. That led to a tiny 1 in a billion excess of matter over antimatter. That tiny excess is everything. The stars, the planets, us. We are the leftover debris from that near-total annihilation. Within the first 3 minutes, the universe cooled enough for protons and neutrons to form, and for nuclear fusion to begin, forging the first atomic nuclei, hydrogen, helium, and trace amounts of lithium. This Big Bang nucleosynthesis was the first cosmic forge, but it was brief. The universe was expanding and cooling too rapidly to create heavier elements. For the next 380,000 years, the universe was a hot, opaque fog of plasma and radiation, a constant battle between radiation pressure and gravity. Then came recombination and the release of the CMB. The universe became transparent, and the so-called Dark Ages began. For millions of years, there were no stars, no sources of light, just the expanding, cooling glow of the CMB and the vast dark clouds of neutral hydrogen and helium gas. But the seeds of violence were already sown. The slightly denser regions imprinted from inflation slowly, over hundreds of millions of years, gathered more and more matter through gravity. The first stars did not form gently. They were behemoths, hundreds of times the mass of our Sun, known as Population 3 stars. The first stars were unlike anything we see today. They formed in isolation from the pure primordial gas of hydrogen and helium. Without heavier elements to help them cool and fragment, they grew to tremendous sizes. They lived spectacularly short and violent lives, burning through their fuel in just a few million years before exploding as supernova or collapsing directly into black holes. These first stellar cataclysms were crucial. They polluted the pristine cosmos with the first heavy elements, carbon, oxygen, iron, forged in their cores and scattered in their depths. This metals enrichment was the necessary step for the formation of rocky planets like Earth and for the eventual emergence of life. The violence of the first stars seeded the universe with the potential for complexity. Gravity continued its work, pulling the first stars and galaxies together. The first black holes, the stellar mass remnants of those first giant stars, began to merge and grow, eventually sinking to the centers of proto-galaxies to become the supermassive black holes we find today. The universe was building itself up hierarchically through a cycle of gravitational collapse, stellar ignition, and supernova destruction, a cycle that began with those initial quantum fluctuations. The story of cosmic structure is the story of gravity amplifying initial violence. The great cosmic web of filaments and voids we see in the universe today is the direct result of the gravitational collapse of those initial density fluctuations over 13.8 billion years. The voids are the regions that were slightly underdense. They have been emptying out ever since. The galaxy clusters and superclusters are the regions that were slightly overdense. They have been gathering matter ever since. This brings my journey full circle. The chaotic orbits of planets, the fury of stars, the terror of black holes, and the collision of galaxies, all of it can be traced back to the quantum scale violence in the first instant of time, magnified by inflation and orchestrated by gravity over billions of years. We are not simply living in a violent universe. We are the products of that violence. The iron in our blood was forged in the heart of a massive star that died in a supernova explosion. The oxygen we breathe was fused in a star that lived and died before our sun was born. The gold in a wedding ring was likely created in the cataclysmic collision of two neutron stars, and the very atoms that make up our bodies were assembled in the fiery crucible of the Big Bang itself.